All right. This is a today, right, class? Distributed database. So today we are here. And next week, we're going to meet on Zoom. Okay, you can come on Zoom. There will be no new lecture, but we are going to wrap up. If you have any question about, no. Yeah, question about homeworks, no, not homeworks. Yeah, final exam, you can bring some questions with you.
The homework 5 is due today. Can you please just extend it 1 day?
Why not? That is your Thanksgiving present.
No, because
Fine. Yeah. So next week we're going to meet on Zoom, but short, maybe 20 minutes, 30 minutes. And then week after that, we're going to have a final exam. Final exam. This time. But I am going to give you online exam. Okay. The questions very similar to the ones that you used to have from me when you took 505. Similar to that. Kripesh, did you take 505 with me? Have you taken any course from me?
No, this is the first class.
Oh, maybe challenging, right?
Yeah, maybe you can give important questions so that I can practice. We can practice.
Bro, come on, don't give him ideas.
Okay. I'll try to find out. Yeah, some sample test. As I mentioned there, it's not going to be in class, so it'll be Zoom. You can log in your Blackboard. Then there will be some of the point that you can get in the exam questions. So usually you need to type there. Less likely multiple choice. Maybe true false type of questions possible, but short answer type of questions will be given to you. Yeah, that is what's left to for this semester. If you have any quick question right now that I can answer to you. Other than that, so today I'll give you a lecture, which will be the last lecture. And then next week, a short meeting to wrap up this class. If you have any question about exam, anything, bring up so that we can resolve any issues. Okay, so that is done. Let me check if it is recording. I am wondering. It is recording because it says stop recording means it is being recorded. Fine. Okay. So distributed query processing. The title here, distributed JSON structure and processing. And also this slide, bottom of each slide, I put there copyright by John Yoon. I'm going to present this work next year, some international conference. So till that time, I want you to keep this. It's not public until that time. So today's lecture, we'll start with JSON structure. JSON, you probably seen the JSON here and there. Definitely, when you took 505 with me, data type. So it could be a dictionary of dictionaries of list. So all nested format of data types. That is a JSON structure. And then we'll look at distributed selection processing and distributed SQL processing and real-time processing. Real-time processing is missing. Right now, I'm still developing, so it's not going to be included today's lecture. But the idea is remains the same. We are looking at JSON data and how we can use that JSON data format for distributed query processing. This isn't the example of very complicated data type. I mean, I would say this is let's see. This is a if you're thinking of database table, then columns and rows. We have column location, east, west, and more rows. And the next columns are a little different from relational database or table-based database. This is more like complicated data structures, because if we say apparel, then apparel can be composed of shorts, outwear, and suitings. And each of these can be decomposed into, for example, by size, small shorts, medium shorts, large shorts, extra large shorts. Similarly, small outwear, medium, large, and extra large outwear. Same thing for suits. And then there's some of the models. S1 is available in East location. I was trying to develop this during our Thanksgiving and Black Friday, Cyber Monday big sales. And Model S1 for small shorts may be available in both locations, East location and West location, right? And some of them are available in one location, but not in another location. So that is the thing. So this kind of complicated, complex complex data types are available anywhere, right? And also in another cases, this case it has 3 depths, right, or 4 depths of the structure. Each item may have different, right? If we are thinking of electronics, then TV and model TV1, TV2, and laptop, then West location has a PC1, PC2, PC3, but not in the East location. Similarly, others. So this slide try to explain the data that we are going to deal with may be very, very complicated in structure. It may not be a simple structure like the ones that we looked at in relational database. Simply flat levels of columns and flat levels of rows. Very, very simple, right? But in reality, the data structures may be complicated like this. How can you deal with this? particularly if data dispersed, distributed in many places. Okay, so that particular example can be hierarchically organized like this. Location east, apparel has a shorts, and this is something like a tree structures. But I didn't make this in tree, but will come later. It's more like in-depth indentation-based some of the containment information displayed here. Location, for example, apparel has shorts and suitings, and short has small, medium, and large, and small has S1. If it is the case of east location, if it is a west location, might have different apparel, shorts and outwear. If you see the difference, east location, shorts and suitings, west location, shorts and outwear, and the size not uniformly identical. They are different, right? Electronic, same thing. East side, we have a TV, sensor, and microcontroller units, but west location has a TV, laptop, and monitor. So very complex of data, content and data structures are represented in JSON formats. So this kind of indentation-based data structures can be depicted in a tree structures. Have you guys heard tree structures in computer science? Tree is one of very useful data structure in computer science. After you learned, for example, dictionary, list, tuple, in the case of Python. But in data structure, there is a tree and network. Those are two major data structures available. The way that you can interpret this data tree structure is this. Tree usually has a root, and then there's a trunk, and then branches, and branch can have another further smaller branches. It keeps going, right? That is tree structure, if you think the trees are out there. The structure that you can see here, that is upside down. Root is on top. So we usually call this root. Root, there is a one root. Okay? In this case, one root has one child. So from top to bottom, we can interpret this root and child and subchild, and child has its own children, right? So this root node has one child node, which is simply open and close square bracket, which is nothing but list in Python. And then this node can have two child nodes. One on left, shoes, one on right, shorts. Between nodes, in different level, which means root levels, and this is one child levels. This is the first child level, and this is the second child levels. Between the level, there is a the link or edge. There's a label of that edge. I call this KV link. What that means is key and value link. Inventory is a key, value is a list. And there is another type of link called C link. C link means containment link. This is my definition. But the idea that you can see this anywhere in tree structures. But when I try to draw JSON data seamlessly, this is a good format of a good tree structure. If this is a list, then list contains shoes. First element in the list, shoes. Second element in the list, called shorts. Good to see you, MD. And the shoes has also a list through KV link. Okay, so this list has containment, something contained in itself, through C link. Regular shoes and special shoes. Regular shoes, then there's a model D1, which is regular, that is key, and then value D1. So key and value pair. So everything here in this structure, key and value pair or containment list. So this is a structure of the tree. In order to define this tree, we need to define also JSON token. Token is either one of the control character. If that is a dictionary, then curly braces, open and close. And if it is a list, then square brackets, open square bracket and close square bracket. So we have 4 control characters plus key and value. Key is, we named K, value V, so that we have a K colon V pair. Example for that is inventory of that, and then I would say here another example. Inventory has this, right? Where oops, sorry. Okay. Is it clear now? So this is example of the tokens, and another examples, key and value pair that I explained here, but I didn't give an example. So JSON tree can be depicted over JSON tokens. So token is a node. JSON path, there's a sequence of JSON tokens that leads to the position of a value. So for example, inventory dot shorts, inventory, there's a key, and value is a list where there is a short. So inventory dot short. Short is a key, and value is in a list where there is a large shorts also. So that is this node. So it'll be inventory dot short dot large. This large has also KB link, a list. There we have H1. So from here, from the root node to the leaf node, so we have, using the dot notation, we have a sequence of the tokens. So inventory dot short dot large dot H1. This is a path. Knowing this path, we know we can see from top to one of the leaf node to bottoms, somewhere here. So we have this kind of a path. So using that, we can build JSON trees. So JSON tree is a hierarchical structure organizing a JSON data set. A JSON tree consists of nodes and edge. So nodes are JSON tokens which are connected by edges. I think I explained already. So node are connected by either TV link or C link. So node is a JSON token. Edge is either KB link or C link. So KB link connects a key to a value. C link shows an array contains values. So it shows which value is contained. So example for that is KB values like this, shoes colon and another dictionary, regular colon, and then we have this. And then C link, regular colon D. Is it D or D1? Maybe D. Then that is C link. Root, topmost node, that we already said that. Ancestor. So because we are talking about the child and child of a child, children of a child, we along these hierarchies. So there is an ancestor. Given one node like special here, what is the ancestor? So if you go up, then shoes and inventory, those two nodes are ancestor. And then the descendant, similarly. Descendant of shorts. Taking these shorts, what are the descendant? So go down here, and then we have to traverse all the elements in the list. So small, medium, and large, and even further those two numbers. So they are the descendant. Each node can have a multiple child nodes recursively. So child of inventory is shoes and shorts. Child of shoes, regular and special. Like we can say child of shorts, then small, medium, large. Leaf node is the node here. Leaf node, in other words, called the value nodes. When you come down leaf node, then you can see the values. Leaf nodes are value nodes, while non-leaf nodes are non-value JSON token. So we have a trees. We consider JSON data. JSON data can be in JSON repositories, and JSON data can be generated from SQL. In your host language, remember that we worked on SQL embedded Python coding, right? Then Python has some function that can take SQL and returns JSON. If you implement a web server in PHP has JSON generator as well, which I developed in our server, which will be used in another course when it comes to mobile technologies. But anyway, there is a JSON data. So JSON data also, JSON documents itself as a single file itself is a JSON data. Or JSON data may be stored in MongoDB or NoSQL database. NoSQL database, MongoDB, the data can be stored in a JSON format. So that is also JSON data. So JSON data is available everywhere. Beauty of JSON data is it's simple to identify what is what. For example, here, this is a JSON data. This is a JSON tree, right? This tree can be represented in this way. Inventory. That is the square bracket. Inventory has a dictionary, first dictionary, and we have two dictionaries, right? From shoes to here, that is one dictionary, and then shorts, that is another dictionary. This is a dictionary. Shorts dictionary, this is a shoes dictionary. No, this is one dictionary, but two elements. Shoes, there is a key, another key in that. No, I don't think we need this, right? With, you can see only okay, this is a little different, right? So this list has shoes and short in a list. So this is the list. So if you see this, I am going to bring up Paizo so that you can see it more clearly. I already made it here in Paizo. You cannot see that. Yeah, this is it. Okay, when I run this, inventory has shoes and shorts. Shoes has regular, special, and shorts has small, medium, and large. So display, this is a function for display, and this is dictionary. Everything here that is a dictionary, this is a dictionary, but if you see inside the dictionary, then see there is the highlight, the character highlighted. Dictionary key is inventory. So inventory is the key. So one element only in this case. Inventory, then there is a the value. For this value, there is another list. In the list, first element is a dictionary. Dictionary start from here, the ending here. First element in the list, that is a dictionary. Second element in that list, there is another dictionary, which is a short. Inventory has a list. It's not displayed here, right? In the list, first element is shoes, second element is shorts. That's what you can see here. If you see inside the shoes, okay, this is the first element. This first element itself is a dictionary, therefore key and value pair. First key is shoes, second key is special. Value for the first key is yet another that is yet another list. In the list, there is a dictionary, one dictionary again, and then dictionary has key and value. Value is a list. So this could be simply a single value to this key, or list of value, which is the value to this key, special. That is also possible. So if we run this, remains the same, right? Doesn't matter this. But if you see, you cannot see. If you see tree, then you can see the difference clearly. We don't have to do this, as we can see here. Okay, that is this. This can be represented in this way. If we have this tree structure, then there is a hierarchical representation so that you can see which ones contained where. You also see key and value pairs. And also the strength of a JSON tree is a multi-cardinality. What does that mean? Multi-cardinality means in relational database, value is usually a single cardinality. If there is one particular column and particular row, then you have atomic value. For example, in the student tables, there is a name. Then first row, the name, student name, first student in the first row, a particular name, like John. Another student on the second row, then name should be another atomic values, like Kripesh. Okay? Uniform in relational database. But in JSON, as you can see here, the value for regular, that is atomic, but value for special, it could be another list. And value for shoes, no, yeah, that's what I'm saying, yeah. Not anymore. I think I need to make it a little more complicated. As you see here, electronic, TV, laptop. Electronic. Oh, there is no electronic here. I think I should have electronic more here. Right? We don't have electronic here. That is the reason, yeah. If we see electronic, then there is another depth. To the leaf node, here to the leaf node, very similar, right? Depth is similar. But if we have electronic here, another, then electronic depth is shorter. What that means is that here the complexity of operals, we have more depth than electronics. Okay, that can be represented in a tree structures very clearly. So we have tree structures anyway, that can be written directly, or that can be generated from SQL database. To handle that, we need to define metadata. So C JSON and D JSON. C JSON, that is JSON tree, and D JSON, something about. It's a collection of leaf nodes, collection of data catalog. What that means is that given node, we have the location. Okay. Each location has different inventories. If you, for example, in Black Friday sales, so you receive the purchase order, then shipping site not necessarily from one location. Depending upon the availability, if you, for example, you purchased shoes and TV sets or a monitor, okay, shoes and monitor, then shoes are available in West location, monitor is available in West, in different location. For one order, but shipping location may be different, depending upon the availability. They don't need to check whether they have, but they simply process it. Whichever available, then it goes to that location and process the deliveries. That is what's happening in reality. But I want to make it formally, like here, distributed JSON database. In the past Black Friday sales, I placed two apparels, one for me and one for my daughter. My daughter's item was shipped from somewhere in Long Island. My jacket, you know the jacket that we had the problem? Jacket with no buttons. It was shipped from Parsippany, New Jersey. Two different sandals appears after I placed the order. I had a little worry, but I trusted that department store. Because this is recorded, I'm not going to say that department store. But anyway, it was delivered on the same day. It shipped from two different, it ordered from me, same order, shipped differently, delivered at the same time by one delivery man. When I opened it, one item okay, the other item, my suits, no buttons. How can I wear jacket with no buttons? So I stopped by this afternoon there. And then, but anyway, will be resolved manually. But they need to be done this automatically, right? With no human's intervention. If there is some issues, then human interventions there. So in order to do that, we need to have this kind of JSON files, collection of data catalogs. So depending upon location, depending upon item, for example, shoes, where there's those models and that size shoes available. So we have a list of the location. Okay, that should be available. Another thing is from top, then we have a JSON path expressions. What is a JSON path? I've already defined it, right? JSON path is, this is a JSON path. Maintenance. So this kind of JSON metadata needs to be maintained. That should be, the thing is this. Let's say your inventory site, you have new items comes in. Then you have to update the data catalog, right? So who can update? So each site needs to update. So which one should be updated? The common JSON data needs to be updated. So it should be located globally. So whoever wants to see the inventory, then they need to see at real time that particular JSON files. Therefore, if one is sold, then that one can be deleted. If there is no nothing, then that should be deleted. So updated by client. Client means each location. By each location. So each location we have to send this kind of JSON data. Then at the global repository site, by reading this JSON data, whatever they have globally, that can be updated. Go here, then this is my location. So if this node is not available, then my location can be removed from here. If I have a new items never stored before, but newly inserted, then it should be updated here. It should be added, appended the list. So this happens updated by each location when completely sold out or the newly registered. There's maintenance. Functions, some functions needs to be defined. So subtree functions can return the subtrees of a given node. What is a subtree? If this is a tree, then subtree is from any node. Let's say what is a subtree of short? Then this itself is a subtree, this part. Given entire trees, subtree can be, for example, this is a node. I wanted this node as a root. Then this is a subtree. So a tree can contain multiple subtrees. This is subtree, which can contain this subtree, and that subtree, which can contain this another subtrees. So that is a subtrees. And update, that I explained here, right? Each location needs to update. And side out and push down. This is something that I am going to explain. Side out, what that means is, if I place the order, that it goes first to one location, right? And there, if particular item is not available, then that tree structure needs to be expanded. Ideally, it is this. When I place an order, then it can come this path, for example, okay? This is the path that I am interested in. Okay, this is the path that I am interested in. But because of the location, because of depending upon the inventories, this is not enough. So I need to expand this. Okay, so it's not clearly completely seen here, but if you have more path trees, then you can go. We can expand this a little further. Starting from the small subtree, we can expand it. We side out, okay? That is what we can do. Push down. Some functions needs to be pushed down. Functions are not available here in these tree structures. So behavioral aspects needs to be pushed down. That's what we can see in the list somewhere here. This is JSON tree and queries. Okay. Two types of queries: JSON path expression query and SQL expression queries. This is simply for given node, there's an expression to indicate sequence of the nodes to express some specific leaf nodes. For example, check the inventory of a laptop. Check the inventory of special shoes. This kind of queries can be formed. Another type of queries is SQL-like queries. We can say select from where clause. So select location. I want to count the medium shorts. How many medium shorts are available depending upon location. So for example, Manhattan location, we have 5 medium shorts. Florida location, we have 3 medium shorts, things like that. So we can say select and from any locations, group by location. This is not real executable SQL expression, but I want to say this is like SQL, right? There's no any location type of tables. If we say from any location, in real SQL statements, we need to list number of tables there, right? From student enrollment, things like that. But if I say any locations, then and group by location. But anyway, this is very similar to SQL expression. That's what I am considering. So if it is a JSON path expression, if we are interested in special shoes only, by looking at this JSON data, some of the bold-faced character, those are items that we are interested in, but that can be shown in this tree along this path, that is what I am interested in, right? From inventory to shoes, special, so that is a special shoes. So I am interested in somewhere here. Either this model E1 or model E2 and so on. So JSON path expression can be shown, can be displayed in JSON tree very clearly, like this. And if you want to see, for example, how many, then first you need to see the JSON path, and then you have to take care of some of the functions. These functions, count is a function that can be done by push down functions. So function, push down functions, there is another dictionary that can contains a list of functions. Each functions, this is a key, and value is this function. This is a real function, right? Values.count. This can be pushed down to that path that we looked at, right? It goes down here. So it actually should be more here. Somewhere here, right? That is what I mean by push down. So function needs to be pushed down. Then it'll be completely like this, path expression followed by functions. In this way, this kind of JSON path expression queries can be processed. On the other hand, SQL expression. So we have tables, I would say here tables. So sample relational database, it has inventory. Inventory has ID and item. Shoes has ID and type model. Shorts has ID, size, and models. And ID is the key. Therefore, any particular shoes that appears in inventory also. Same ID, right? In different tables. If it is a SQL database, then we look at only particularly regular. Here, select a star from subtree inventory where leafnode.kb link not exist and leafnode.c link not exist. What that means is that there is no nothing. Only these tree structures available, but there is no values. What does that mean? No inventory, right? Particular location, there is no inventories. Therefore, they need to make a quick order. So it can shown like this in the tree structures. So distributed assumption is this SQL expression processing and JSON path expression processing. We looked at two different processings. Now we can extend that to distributed fashions. Although I explained it in many cases some of the distribution assumptions. But anyway, if data are distributed, then data can be distributed by partitioning. Table can be partitioned horizontally. For example, if I partition this in this horizontal, then shoes, some of the shorts and outwear may be in one location. For example, if I do partition I want to partition somewhere here. Okay, so I want to see should be red. Okay, I want to partition here. Then left side there may be one in one location, and right side in another location. That is a vertical partitioning. Similarly, we have horizontal partitioning, right? So here and there, all the way to the end. So this row may be in one location and the other one is in another location. Or combination of those two. So it could be here, that is one location. And maybe this is on another location. Oops. Another location. So this is one location. This is another location. This is another location. Another location. So 4 locations maybe hold different items. So if you receive an order, then one order may consist of one item there, another item here, another item over there, another item over there, right? But it comes from this one request. Request is nothing but a query, right? So that kind of query needs to be handled nicely in this distributed fashion. That's what we are looking at here. Distributed query processing. So we have operations. Distributed query processing. We have a catalog assumption. So catalog, shorts catalog can be assumed in this JSON data where there is a medium shorts G2 is available in location 1 and location 2, and large shorts in model H1 available in location 2 and location 3, and so on and so forth. That type of JSON data, JSON metadata available at the global repositories about shorts, then if we have this kind of distributed query from SQL embedded query expression, this is a query. Query says select location and number of item counts, quantity of particular item from inventory, where medium shorts in model G1 is greater than 35. 35 may be price. So expensive medium shorts, is there available? Then medium shorts in G2 if we see here, then location 1 and location 2, right? So in this for loop, this is a query language, Python, right? For each in catalog of shorts, colon, db cursor, we have the cursor dot executes, and dq1. dq1 is this entire query language. All right, I think this is something that we have to say. Percent, right? Therefore, instead of this percent, one time, one location, log1 can be placed in here, and at another query language, then log2 can be here. So it'll be like this. So it'll be log1 from log1 from log2, location 2. We have the same SQL language, but we union them. Two SQL languages can be unioned. In that way, given one SQL language, it can be expanded. We call that side out. One SQL language can be extended from this SQL language to that SQL language, side out, and union them. And we create them as a view, and that view is in SQL. This is a view creation. So we first create view, and that view is in this SQL statements. Okay. Another thing is embedding unions. This first one is to create view first and use the views. Second one, we don't need to create views. We simply use it directly. So select t.location and count from. In this from clause, we have everything of that. Union. Two SQL are unioned together as a one table. Table name is in from close, and then we call that T. That is acronym or alias. That T, so we group by t.location, and that t.location is selected, that listed, t.location and counts. What that means is that the location number, location name, east, west, central, and then there's in one column, another column, how many? Okay, that type of things can be returned. I know this is a broad concept of distributed query processing based on JSON format data. But this may help you when you consider distribution. So not only distribution, but processing on that distributed data. This is the end of my lecture today.